Hello, everyone. Today I'm going to talk about our work on a multimodal large language model for material property analysis. So I'll start with our motivation. Yeah, this slide I briefly state a timeline for the existing method that we're using for material property analysis. Here we have the traditional computational methods like DFTs. Those are accurate, but generally they are computationally expensive. And then we have physics ML models, but they are fast, but they're typically designed for specific tasks and the lack of the interpretation abilities. And recently, more and more people and scientists have been using LLM to solve scientific and non-scientific problems. However, in material area, the material always comes as a structure. So one typical approach utilizing LLM for this such task is that we first make the conversion from the structure to its crystallographic data, and then tokenize them and feed them as a sequence into the LLMs. Even though the first conversion step from structure to crystallograph data is reciprocal and lossless, but the second step, when we tokenize everything into the LLMs, often fails to leverage the spatial relationship in the structure directly. And another thing is that the LLMs typically commonly lacks of numerical precision, makes it limited for some highly quantitative tasks. So essentially, this project, we're trying to design an approach that can effectively combine the material structure data with the text form of data and utilizing LLM to better solve the material property analysis. So this slide shows the overall structure of our model. So generally, our model is comprised of three branches: the material structure processing branch, the language processing branch, and the bridge model. So the material will be first converted to graph and then feed into the physics graphic encoder to get the atomic embeddings. And the atomic embeddings will be fed into the bridge model, which is a transformer-based model where the trainable queries will do cross attention with the atomic embeddings to further extract the features, and then passing through a projection layer to get the final query embeddings, which are dimensionally compatible with the language embeddings. Here, the language embeddings are coming directly from the user prompt. In the text version, user can prompt questions such as, what is the chemical formula of the material? What is the formation energy of the material, etc. And then the language embeddings were combined with the query embeddings feeding to the LLMs, and LLMs will generate the output. So this slide shows the general training scheme and the overview of the data set that we're using. So for training, we're implementing two-step training. So phase one is the pre-training, where we're using the bridge model with the frozen graphic encoder, where we're taking the material structures along with its description test to form an initial alignment between the structure and the text. And then for the second step, it will be the end-to-end multimodal instructive fine-tuning, where we loop the LLM into the training loop and train with both description task and the property tasks. And the right panel shows the data set, or the overview of the data set that we're using. So we essentially curated the data set from the LBL's material project database. And currently we're using around 140,000 different materials. And the bottom periodic table with color map shows the chemical composition distribution for all the material structure samples that we use. Yeah, in this slide, we're providing several qualitative, interactive user AI interaction samples using our models. The left panel shows our model is able to take dual models of data, which is the structure, along with the user prompt to solve various material property questions, such as the chemical compositions, space group, thermal stability, band gap, magnetic order. And the middle panel we're trying to show here is like our model is able to utilize the inherited knowledge in the pre-trained LLM to providing more insight for some downstream material tasks. And the example we're using here is one common semiconductor material, gallium nitride. As you can see, the model is able to provide a detailed description along with a step-by-step synthesizing guidance for such material. And the right panel is like we selected one of the newly discovered stable material from DeepMind last year, and we're trying to query the formation energy using our model, and we also compare it with some existing commercial LLMs, including Gemini, GPT, and DeepSeek. As you can see, our model can predict the relatively accurate result, very close to the ground truth here. This slide is, I want to present is some like a visualization to further prove that our model can efficiently integrate the structured information. So here we selected the material samples from the material data set containing silicon and carbon composition, and then we extract the embeddings using our models, and then perform the visualization through dimension reduction technique. Here we're using UMAP, and then making a 2D plot to show the clustering. So here for different samples, we're using two metric to color map it. One is based on structure similarity. The other is based on formation energy. As you can see, the visualization shows clear clustering, not just for different chemical compositions, but for same compositions with different crystalline structures. And the right panel shows there is also existing clear clustering based on the energy distribution, where the samples have clear distribution in low energy region and high energy region. So this finding support us to incorporate the multimodal RAG during our inference to further enhance the model's performance. So here, instead of like directly getting the output from the single input through the model, we're adding two steps. One is the retrieval, the second is the aggregation. So in the retrieval phase, we are seeking similar structures from the material database. Here could be our training set through the L2 similarity scores to measure the similarity between our input structure embeddings to the materials in the material database, to getting instead of getting one response, we're getting various responses. So after getting various responses, we aggregate all of the response to get the final output. So the aggregation strategy that we're using here is like for classification task, we use a max count, and for regression task, we're using average. So this slide shows that we perform some like a quantitative performance comparison across various material property tasks, and we're evaluating in several LLM models and the physical ML models and our models. And essentially, we're testing across all the material property tasks on the evaluation data set, which is around 14,000. And the first two rows are all classification tests, and we're using accuracy as our evaluation metric. So the higher the value, the better. And the bottom rows are for our regression test, where we measure the energies and band gaps. So we're using RMSE loss as the evaluation metric. So the lower the value, the better. So overall, our model achieved the very good performance across all of the tasks on average. So in summary, we're introducing MetaChat, a multimodal LLM for material property analysis, and we demonstrated superior performance through various qualitative examples and quantitative chart. As for future work, we're currently thinking of three directions. First is to expanding the QA pair to make it more comprehensive. Second, so we're thinking of making a domain-specific fine-tuned LLM, which are tailor-made for the material science applications. And we're also thinking of adding a generative model to generate new materials, which will be benefited for new material discovery better. Yeah, so in the end, a special acknowledgement to the NERSC GenAI program. We get a huge amount of node hours from them, which makes this project possible. Yeah, that's it. Thanks.